Hello. Today I want to cover part 8 of my series on essential theorems for harmonic astrology. So let's see if I can share my screen and we'll get started. This will take just a few seconds. I get rid of some things so I can see what I'm doing. And I'm almost there. Hold on. And we're there. So this is essential theorems for harmonic astrology, part 8, positive rational number harmonics. Okay. First, let me restate Theorem 6 from the previous video. And Theorem 6 said, given any angle theta, such that 0 degrees is less than or equal to theta less than 360 degrees, and any natural number k equal to m times n, where m and n are also natural numbers, then the k harmonic is identical to the m harmonic chart of the n harmonic chart. So that says that when we're dealing with natural numbers, we can do these in order kind of consecutively. You could compute the k harmonic chart all at once, or you could first find the n harmonic chart and then the m harmonic chart of that result. Well, even though Theorem 6, which is proved in our previous video, doesn't hold for all positive rational numbers, does hold for natural numbers, there are nonetheless important connections between natural number harmonics and other positive rational number harmonics, as the theorems that follow will show. So, Theorem 7. If n over m is a positive rational number in lowest terms, where n and m are natural numbers, then the root n over m harmonic angle is also a n harmonic angle equal to m times 360 degrees over n, and then that result reduced, if needed, modulo 360 degrees. And for the proof, well, since the root n over m harmonic angle is 360 degrees divided by n over m, modulo 360 degrees, well, you can just algebraically flip this fraction and rewrite that as m times 360 degrees over n, modulo 360 degrees, and the result immediately follows. And what this shows us is that the n over m harmonic angle is also an n harmonic angle, since we just simply take a natural number multiple of this root n harmonic angle. We multiply that by m, it's still going to be some sort of n harmonic angle. Okay, so these positive rational number harmonics can actually be reduced to multiples, natural number multiples of natural number harmonics. Okay, I might note that since every positive rational number can be written in the form n over m, where n and m are natural numbers and n over m is in lowest terms, we emphasize that the above theorem applies to all positive rational numbers. Hence, under these conditions, the n over m root harmonic angle is also an n harmonic angle. Not necessarily the root n harmonic angle, but some natural number multiple of it reduced modulo 360. The next theorem will take things further by showing that the n over m harmonic angles in their natural order, which I denote by h sub n over m, are just a permutation of the natural ordering for the n harmonic angles, i.e. h sub n. So, Theorem 8. If n over m is a positive rational number in lowest terms, where n and m are natural numbers, then multiplying the root n over m harmonic angle in turn by the numbers 1, 2, 3, all the way up to n creates a permutation of the usual ordering for the n harmonic angles. In other words, a permutation of theta sub n equal to 360 degrees over n. This will be the root n harmonic angle. Now, actually, one slight correction here. If n is 1, excuse me, then this comes out to 360 degrees, and you got to reduce that modulo 360 to 0 degrees to get theta sub 1. But for n greater than 1, this is already going to be below 360 degrees, so you don't have to reduce it modulo 360 degrees. So we take this as our root n harmonic angle, certainly true for n greater than or equal to 2. Then you multiply it by 2, 3, and so on, all the way out to n, which gives you something equivalent to 0 degrees. And that is the usual natural ordering for our n harmonic angles. Okay, let's take a look at the proof here. Let's let theta sub n over m equal 360 degrees divided by n over m, modulo 360 degrees. So this is going to be the root n over m harmonic angle, and that is going to be equal to m times 360 degrees over n when you flip this fraction, and then you evaluate it modulo 360 degrees. Where n over m is in lowest terms, we'll assume that. Then note, as shown in Theorem 7, theta sub n is both a n over m root harmonic angle and also a n harmonic angle. Consequently, every natural number multiple of n over m reduced modulo 360 degrees is also both a n over m harmonic angle and a n harmonic angle. Okay, now since theta sub n over m is also an n harmonic angle, it follows from Theorem 5 that if you do n times this n over m root harmonic angle, reduce the result modulo 360 degrees, you get 0 degrees. Now suppose that t is the smallest natural number such that t times theta sub n over m modulo 360 degrees is equal to 0 degrees. Then clearly t is going to be less than or equal to n. If t is less than n, then 0 degrees is equal to t times theta sub n over n modulo 360 degrees. But you could rewrite this as t times n times 360 degrees over n modulo 360 degrees. But this implies that n divides into t times m, right? If this is going to come out equal to 0, then this part here has to be some whole number multiple of 360 degrees, so you got to be able to divide n into this mess. Well, this in turn implies that a non-trivial factor of t times a non-trivial factor of m is equal to n. You can't have n dividing entirely into t because we're assuming that t is smaller than n. Okay. However, this last statement implies that m and n contain a non-trivial common factor, which in turn contradicts our assumption that n over m is in lowest terms. Hence, t must be equal to n. So n is going to be the smallest natural number. We can multiply this root n over m harmonic angle by in order to get back 0 degrees when we reduce it modulo 360 degrees. Okay, well, if t is equal to n, that means that multiplying the root n over m harmonic angle, theta sub n over m, by the numbers 1 through n results in n distinct n over m harmonic angles, which we can list as theta sub n over m, 2 times that, modulo 360 degrees, 3 times that, modulo 60 degrees, all the way up to n times this modulo 360 degrees, which will be equal to 0 degrees. Okay. theta sub n over m, this is already reduced modulo 360 degrees since it's the root n over m harmonic. And when I multiply that angle by numbers which are smaller than n, I don't get back 0 degrees yet, because that's what we proved up here. The smallest number you can multiply that to get back 0 degrees when you do it modulo 360 degrees is going to be n. So I've got n distinct n over m harmonic angles, but these are also going to be n distinct n harmonic angles. Okay, I think that's why I say here, but again, since each n over m harmonic angle is also a n harmonic angle, it follows that the n distinct n over m harmonic angles must be the same as the n distinct n harmonic angles, but in a possibly different order, where k times theta sub n over m modulo 360 degrees is computed in the order corresponding to k equal 1 through n. Therefore, the n over m harmonic angles in their natural order are simply a permutation of the n harmonic angles. Okay? Now, let me point out that if m is equal to 1, then theta sub n over m is just equal to theta sub n, and you get back your n over m harmonic angles in the same natural order as the n harmonic angles. In that case, we would still say it's a permutation. We just call it the identity permutation. That means we haven't changed the original identity in any way. So even with m equal to 1, we'll still say that we get back a permutation of those n harmonic angles. It just may be the same permutation, the identity permutation. Now, let's look at corollary 8.1. If m and n are natural numbers, and if n over m is in lowest terms, then the number of n over m harmonic angles is equal to n, the number of n harmonic angles, and every n over m harmonic angle is also a n harmonic angle. This is simply a formal restatement of some of the things that came to light in proving Theorem 8. So it's really just another way of looking at Theorem 8. All right. Let's recall that the set of n harmonic angles in their natural order, beginning with the root n harmonic angle and ending with 0 degrees, is denoted by h sub n, while the set of n over m harmonic angles in their natural order is denoted by h sub n over m. As ordered sets, these two contain the same elements, but in possibly different orders. One consequence of this is that natural number harmonics may be all that matters, since every n over m harmonic angle is also a n harmonic angle. Recall, too, that when graphed on a 360-degree circle, the n harmonic angles define a regular n-sided polygon for n greater than 2. In a similar manner, if n over m is in lowest terms and m is not equal to 1, then the corresponding graphs of the n over m harmonic angles and h sub n over m often form a star shape called a star polygon. Not necessarily all the time, but let's say most of the time. Examples are shown below for h sub 12 over 5 and h sub 12 over 7, and the root harmonic angle is denoted or is indicated by a blue arrow. Okay, so this is the star that we get for h sub 12 over 5. Now the 12th harmonic angle, the root 12th harmonic angle, is 30 degrees. So the root harmonic angle here is going to be 5 times that, which is going to be 150 degrees. So our root 12 over 5 harmonic angle is 150 degrees. That takes us to here. And we just take multiples of that, reduce each one modulo 360 if needed. So it goes by multiples of 150 degrees. So we go from here to here to here to here to here to here, over here, down here, up here, back down here, up here, and then finally you get back to 0 degrees. Likewise, for 8 sub 12 over 7, the root harmonic angle here is going to be 7 times the root 12 harmonic angle, which is 30 degrees. So 7 times 30 degrees is 210 degrees. So we'll start at 0 degrees. We go out to 210 degrees, which is 0 degrees Scorpio. You follow that by another 210 degrees. You wind up here, then over here, 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 over here, to here, to here, to here, to here, and then finally back to 0. Okay, so in each instance, we got a star polygon. The polygons look the same, but we trace them out in different orders in this case. And in each of these two cases, we got back all 12 of the 12 harmonic angles. They're just in a different order. We don't start with 30 degrees and go 30, 60, 90, 120, etc. Instead, in this case, we start with 210 degrees, add another 210 degrees to that, and reduce it modulo 360. And, that is going to be how it goes. Okay. Now, one more theorem we want to prove about positive rational number harmonics will allow us to assert things like the equality between the 3/5 harmonic and the 3/2 harmonic. Now, aside from it just being mathematically important to know that such an equality exists, an advantage of all of this is going to be that we can replace every positive rational number harmonic, which is less than 1, with a corresponding positive rational number harmonic, which is greater than 1. And that's going to make some calculations and some proofs simpler. For example, if I divide 360 degrees by something less than 1, I get back a result bigger than 360 degrees. I got to go to the trouble of reducing that modulo 360 degrees. But if I'm dividing 360 degrees by something already bigger than 1, I don't need to do any additional reductions to get the result between 0 and 360 degrees. Okay, so theorem 9, if n and m are natural numbers, with n over m in lowest terms, and if we write m as p times n plus r, where p and r are whole numbers and r less than n, then r is not equal to 0, and 360 degrees divided by n over m modulo 360, that will be equal to r times 360 degrees over n, which is the same as 360 degrees divided by n over r, which is 360 degrees divided by n over r modulo 360 degrees, which is 360 degrees divided by n divided by m modulo p, whole thing modulo 360 degrees. Okay, that's really a mouthful. So let's see what's going on here. Basically, we have n over m in lowest terms. If you try and divide n into m, it will go in some whole number amount of times. It could go in 0 times, in which case you get m as the remainder. But if m is bigger than n, it goes in here at least once. And so you could write m as a whole number times n plus whatever that remainder is. And that remainder is always going to be strictly less than n. And if this is in lowest terms, then certainly n will not divide evenly into m, so you always get back a remainder that is going to be different from 0. Okay, and then we're claiming that this result modulo 360 is going to be equal to all of this. Well, let's see if we can prove that. Well, clearly, 360 degrees divided by n over m modulo 360 degrees. You can flip this fraction, put the m up above, and write that as m times 360 degrees over m modulo 360 degrees. Now, m itself, remember, we can write that as Pn plus r for some whole number p. So we replace this m by that, and that's multiplied by 360 degrees over n. And then it's all reduced modulo 360 degrees. All right, if I multiply through by 360 degrees over n, well, n over n is going to cancel. That leaves us with p times 360 degrees. And then we have plus r times 360 degrees over n. This whole thing reduced modulo 360. Well, since this is a whole number multiple of 360 degrees, when we reduce this modulo 360, the remainder of this part is 0, so this term here is going to be all that matters when we do that reduction. So this is equal to r times 360 degrees over n, modulo 360 degrees, and I claim that this is going to be equal to r times 360 degrees over n, that there's no further reduction that has to be done. And how do we know that? Well, r is less than n. So r over n is going to be less than 1. So we're just multiplying 360 degrees by some fraction, which is less than 1, and that gives us something smaller. So in particular, r times 360 degrees is going to be greater than or equal to 0 degrees, but less than 360 degrees. Furthermore, since n over m is in lowest terms, it follows that m is not divisible by n, right? And that is the reason why this remainder is not equal to 0. Okay, consequently, 360 degrees over n over m modulo 360 degrees. That's what we started out with here. And that is going to be equal to what we ended up with, which was r times 360 degrees over n. Well, this expression, you can move that r back down to this denominator here, rewrite this as 360 degrees, all divided by n over r. We know that this is going to be less than 360 degrees, but nonetheless, we could rewrite that as 360 degrees divided by n over r, modulo 360 degrees, and then r is the remainder that we get when we divide m by p. So we can replace r by m modulo p. So we get that this expression here is equal to 360 degrees divided by n over m modulo p, whole thing reduced modulo 360 degrees. Okay, that's quite a bit. So what does this mean? In other words, if n over m is a rational number in lowest terms with m greater than n, and that's going to make this fraction less than 1, and if r is the non-zero remainder when m is divided by n, so you just divide n into m, then the root n over m harmonic is the same as the root n over r harmonic. You can replace m by the remainder when you divide n into m. Another way to denote this is by saying that h sub n over m is equal to h sub n over r, where r is that remainder. In particular, h sub 3/5 is equal to h Sub 3 halves. You divide 3 into 5, you get a remainder of 2, so this is equal to h sub 3 divided by 2. That's what our theorem says. And h sub 3/4 is equal to h sub 3 over 1, and 3 over 1 reduces to 3. 1 is remainder when you divide 3 into 4. So we can always replace this fraction, which is less than 1, by a corresponding fraction, which is greater than, or actually greater than, greater than 1. Well, I guess if you had, let's see, both n and m equal to 1, you can make this come out equal to 1. So let's say greater than or equal to 1. That is going to make our computations easier. Okay. And it looks like that is the end of it. So I'll stop sharing my screen. And I'm back. So that is part 8 of the series on essential theorems for harmonic astrology. And I hope you join me again for part 9. But for now, I'll just say so long and be well.